enhance your production of your well throughout its life. So today's presenters are Ryan and Michael. A quick brief for the two. Ryan is the OneSteam Technology Domain Manager for North America, where he supports new technology rollouts in the Rockies in Canada. In addition to his work in well stimulation, he has been studying organic and inorganic chemistry for flowback and production fluids for 24 different unconventional formations throughout the world during his last 12 years. Ryan was a key member in developing Schlumberger's avant-garde services, and he will share with us how multi-phase flow meters can also be used to study plug drill out operations. He will show us how theoretical basis for needing to control plug drill outs and what acquired data suggests and what solutions can be potentially implemented. Later during the presentation, Ryan will hand over to Michael. Michael Mikovic is the testing, product, and service delivery manager. He supports the operations for North America land.
Vance, if my dogs come see me, they probably think I'm a bit crazy right now, and especially if I say the word ball drop in this presentation, they're definitely going to come see me. So hopefully that won't happen. So we're going to be talking about plug drill outs today. I'm going to start by spending some time talking about the damage that can occur when underbalanced drilling events happen. Underbalanced drilling is, in a lot of ways, very similar to producing a well. So we should start with a quick overview of our secure operating envelopes, or SOEs for short, which is shown on this slide here. Bear with me for a few minutes, as you'll eventually see why this applies to the plug drill outs. These were developed to help us understand proppant mobilization during flowback and production, but we quickly realized that it was also applicable to plug drill outs. At the bottom of the slide, you'll see an example of an SOE, and on top you'll see a few cartoons that depict what the different zones within the SOE mean. The y-axis shows bottom hole pressure with closure pressure at the very top, and the x-axis shows production rate. So let's consider the flow rates for a few minutes. So on the far left, we have where we're trying to produce a well. We want to make sure that the flow rate is high enough that we can lift any solids to the surface. This is essentially just a computation of Stokes' law. Smaller particles need less flow rate, larger particles need more. Now, eventually we want to make sure that we have all the fluid mobilized, but we don't want to mobilize any of the proppant from our near wellbore zone. So we can compute the limits that will define this area. This is our green zone. So this makes sure we don't mobilize any proppant at all, but eventually we'll reach a rate that is high enough to start mobilizing proppant. And this is what happens when we get into the yellow zone. So we reach a critical rate that leads to proppant mobilization. This is that interface between the green and the yellow. And eventually, if we flow at higher and higher rates, we'll eventually get to the point where we get to the red zone. In the yellow, fortunately, there's not enough stress on the proppant during the lifetime of the well to lead to fracture closure. But if you get into the red zone on the right, that's no longer the case. If a well is operated out in the red zone, it will lead to losses in well productivity. The fractures will become depropped enough that closure can occur. And I'll show an example of this later. But let's dive a little bit deeper into what happens in the secure operating envelope. So if we imagine a transverse propped fracture down on the bottom right, like we show here, since we have converging flow at the casing, if we flow too aggressively, we'll start to get proppant mobilization in the near wellbore region. And as I mentioned before, eventually that can lead to fracture closure. But that depropping event is a function of several parameters, such as the proppant type. If you have very small proppant, it has very low conductivity. Very large proppant, you have high conductivity. It's also a function of the fluid moving through the proppant pack. So if you had a slick water versus a maybe poorly broken gel, those are going to have a very different effect on the amount of proppant that gets moved. It's also a function of frac width and so on. Now, initially, this loss of proppant from the near wellbore zone may not be a problem, because you may have a very high bottom hole pressure. There will not be enough effective stress for the fracture to close in the near wellbore zone. Now, eventually, as the well is produced and pressure decreases, enough stress will build up so that closure can occur, and that can be calculated from the geomechanical properties of the rock. This calculation is shown by the red curve, or a pinch-out curve. So let's show a little It's the curve moving in the bottom right corner from about halfway up in the x-axis to about halfway up the y-axis. So this closure curve allows us to predict when closure will occur. Put simply, the more flow rate we have, the bigger the unpropped cavity create. And the bigger the cavity, the less effective stress we need to close off. That's why that curve moves from the bottom left to the upper right. And it does so with rate. The difference between the bottom hole pressure and closure pressure, or the minimum horizontal stress, is lower up in that top right corner. So of course, we still have the other areas we talked about, the green zone and the yellow zone as well. So let's see the implementation of the secure operating envelope in practice real quick. So here we have an SOE that was developed for a well in the Permian. So you can see that for this particular scenario, the closure pressure is about 7,000 PSI. We have the limits of the well being able to handle a flow of up to 2,000 barrels per day without leading to proppant mobilization. And we can already predict when this is going to happen before the well is even fracked. So this can be designed from the very beginning. We can see that also this particular well, if it gets beyond about 2,600 barrels per day, we should start to see proppant mobilization. Now you can see in the left, you can see all the data points of the well when it was brought online in green. You can see that this well was produced much more aggressively than it should have. It should have only gone up to 2,600 barrels per day at most, but it went beyond 3,700. So on the right, we can show the rate transient analysis. So in pink, you've got bottom hole pressure, and then in blue, we've got the reverse productivity index. So already at this point, we can use the closure curves. So here we have the maximum rate that was achieved for this well at 3,600 barrels per day. If we use the pinch out curve we discussed, we can predict when the fractures that became depropped will eventually close. If we trace straight down from that rate and then to the left, we can predict that we will lose connectivity at about 3,600 PSI bottom hole pressure. Now, it's important to note that this depropping event is when the damage has occurred, even though it technically created a channel with even higher conductivity than it had before. The damage has occurred here, but it doesn't manifest itself until later on. Now, looking at the data from after this maximum rate was achieved, we see that we eventually draw down the well enough that the bottom hole pressure reaches our predicted level. And we should start to see a loss in fracture connectivity at this point, as the fracture closes, as shown in that little cartoon. But at that point, there was no change in the slope of the reverse productivity index and suggested no change in well performance. But once we reach that bottom hole pressure, we see a sharp change in the reservoir performance for the worse. And this is a behavior that we have noted in multiple different formations, and it's not unique to the Permian. So what does this have to do with plug drill outs? Well, let's consider what happens during a standard plug drill out operation with coiled tubing. Plugs are drilled out from heel to toe, with the balance rate being computed per the equation up in the top right corner. If we inject what we get back, we're on balance. Now, of course, there's a swabbing component associated with the bit going in or out of hole, but let's just keep it simple for this discussion. So if our return rate is higher than our injection rate, then we're drilling under balance. And importantly, the additional fluid comes from the fractures. This is where the SOE applies because it's very similar to production during flowback and in later production. This is also where we can determine if the level of underbalance is too high for the well at the time when the underbalance drilling occurs. So let's throw some numbers in the mix so we can further illustrate what actually happens here. So let's say we're injecting at 3 barrels per minute and we return 3.5 barrels per minute. So we have an underbalance rate of 1/2 barrel per minute. Now that's very common, and it equates to a production rate from the fractures of 720 barrels per day. Now, if we're encountering this level of underbalance when we have all the plug removes, it's likely fine. The example we just showed said we could handle all the way up to 2,000 barrels per day. So that's no big deal when all the plugs are drilled out. But if we're in the heel and only some of the stages have been cleared, we probably aren't. If we only had 3 stages and 9 fractures open, for example, the rate per fracture would be equivalent to 80 barrels per day. Now, to give you some context to this, on the bottom left corner, we show kind of sort of typical rates for maximum rates per fracture for 2040 sand and 4070. So 80 barrels per day is far beyond really any standard proppant type is going to be able to handle. Okay, so now that we understand proppant mobilization, how it could occur, and how it could be predicted, let's see what happens when we look at data captured during the drill and operations themselves. So this is an example showing the amount of proppant recovered as measured with a VX meter by stage along the lateral. Now, you might be asking yourself, are these amounts large or small, right? We're only getting, maybe on average about 1,000 pounds per stage. Well, if you're in completions like myself and you know the amount of proppant pumped per well, these seem like very small amounts and seemingly innocuous, right? It shouldn't really impact the productivity of the well. But we've already covered how proppant mobilization from the near wellbore damages productivity, and we want to remove that and avoid that if at all possible. So here's the kicker for this data set and why these seemingly small amounts of proppant matter. The amount of proppant you're looking at here would completely fill the lateral plus a little bit extra. So even though it looks like a small amount, it is actually a huge amount. So there were no screen out events for this well, and it wasn't full of sand when we started drilling the well. So really there's no way to get around the fact that there was sand produced from the fractures. Even though there was some that we certainly needed to clean out, there's simply no getting around that a large portion of it came from the fractures. This is precisely where we do not want the sand to come from. So you probably also noticed that the amount of proppant recovered per stage is non-uniform. Now this could simply be that the drillers went underbalanced more during some stages versus others, but it could indicate something else. For someone who designs completions, this could be very useful information. For example, if we created uniform fractures within a stage, with all of them having the same propped frac width, they should distribute all the underbalanced drilling-induced production equally and produce less proppant overall. If we have a few dominant fractures within a stage flanked by others that are very thin, let's say we have very low cluster efficiency or something like that, we would expect those thin fractures to become depropped very easily since they can't sustain much flow. Their fracture widths would be very small. If paired with lateral logs, we could also find that initiating fractures within a certain rock type would preferentially lead to proppant mobilization and loss of connectivity. Regardless of the mechanism, though, producing this much proppant leads to other issues. So because of the proppant produced, short trips back to the heel produced a lot of proppant. They're also followed by a short circulation period and are often required to keep the CT string from getting stuck. Now you can see the amount of proppant recovered during each short trip in orange, and they dwarf the proppant recovered during each stage. Now, did we produce the proppant during this short trip itself? Maybe, but the more likely explanation is that we didn't actually recover all the proppant that was produced as we were drilling out the stages. We've seen plenty of examples of this, and it indicates that proppant transport in the annulus was inefficient. This leads to duning behind the bit, and if you get too much duning, your bit gets stuck. Now, if too much of this happens, we do get stuck, but by using this type of data, we could experiment a bit and quickly identify which types of drilling fluids are most efficient at removing the proppant from the lateral and bringing it to surface. We could test the effectiveness, for example, of gel slugs, foam, increased annular velocities, and so on to find a solution that could effectively transport the proppant to surface and potentially decrease the drilling times dramatically by reducing the amount of times you need to do short trips, or even by reducing them altogether. Now, before I move to the next slide, I would like for you to have a look at the relationship between the blue columns and the orange columns. Now, if we effectively remove the proppant from the lateral within each stage, the orange columns should be 0. If we don't, they'll be large. This suggests a correlation between the two should exist if we have inefficient proppant transport. More blue should mean more orange if the transport is indeed inefficient. So on this next slide, I've plotted the amount of proppant produced by the stages drilled between short trips. So all the blue columns between the orange columns are in the x-axis. and the amount of proppant recovered during the following short trip is in the y-axis. And we see a very strong correlation between these two data sets, and this makes sense. If we produce a lot of proppant from our fractures and inefficiently transport that proppant along the lateral, our short trip will recover more proppant because there's more to sweep out. This is what we can potentially fix, and a lot of time can be regained during this process by eliminating these types of things. Okay, fine, but what's causing the proppant to be mobilized in the first place? So on the next slide, we show a very busy slide, and I apologize in advance, but we do need to go over this because it's a very important data set, and it illustrates exactly why we need to really have control during this operation. So this is data acquired by a VX meter. Mike, can you go back? There we go. This is data acquired by a VX meter in real time during a plug drill out operation. This is with coiled tubing. The green line up at the top shows injection rate. The blue line shows the return rate, the jagged one in blue. And then balance rate, which also incorporates the swabbing component, is shown in the shaded purple. Anything shaded purple over the red line in the middle is over balance drilling, and anything under is under balance drilling. The depth of the bit as we're moving from heel to toe is shown in black, and the proppant recovered at surface is shown in orange. Now, because we know the return rate, we can calculate the transit time of a fluid associated with a bottom hole event, such as a well surge, when that fluid will show up at surface. Now, because of this, we can correlate what comes to surface with what happened downhole. So let's look at the underbalanced drilling at time x1. So you can see we're underbalanced at this point, and this should lead to proppant mobilization because the fractures, the flow rate for the fractures at that point was too high, and proppant mobilization would be expected. Sure enough, it led to a huge proppant slug later on. And if you look at the, if you trace down with the dashed red line, you can see the double-sided arrow. If you go to the right-hand side of the double-sided arrow, you can see the sand peak that showed up at surface. That when we back calculated, that's the sand peak that actually occurred when we went underbalanced. So another couple of events happened right around time x2 with the same sort of effect. Now, not all of the proppant slugs were associated with underbalanced drilling. Some were simply proppant deposits that were encountered by the bit and were properly cleaned out from the wellbore. Those are good. Those are the ones we want, and we want the entire operation to consist of only those types of events. Now, if we could eliminate or reduce the underbalanced drilling events, most of which fall into the red zone of the SOE in the top right corner, right? So here's the same data, but plotted on an SOE. You can see if we can keep everything in the green and the orange, we make sure that we don't incur any damage in the well. We can reduce the frequency of stuck bits by having less proppant in the wellbore. We can lessen the damage that the well incurs before flowback starts. And there's less proppant that needs to be trucked away and disposed of. So really there's just positives all the way around by eliminating these sorts of events. Finally, here's an example of what excessive proppant production and inefficient proppant transport will cause, and that's simply just NPT. So here's a case where significant underbalance drilling happened early in the process, led to significant proppant production issues that nearly caused the bit to get stuck. They had to circulate the well for 6 hours as a result to sweep everything out, and unnecessary NPT was incurred. So I'll be talking about the mechanisms for proppant mobilization, how we can interpret the data, what problems are caused by this. Mike will now talk about the VX meter itself, which is key to these determinations. We'll talk about how the measurement's made, how it can be used to sense other surface events that we haven't covered, and he can talk about some of the other interesting things we've seen on surface. So Mike, I'll hand it over to you.
Hey, can everybody hear me?
Yeah, we can hear you.
Very good, very good. Well, thanks for the introduction, Ryan. My name is Michael Mikovic, and I'm going to go through some of the operational aspects of the multi-phase meter itself. The VX Spectra, it's really a simple device with very minimal components, none of which are mechanical. The multi-phase meter, it has a Venturi section attached with a multi-variable transmitter that gives us our mass rate. We then have a barium source and a gamma detector, which gives us our fractional measurements of oil, water, and gas. We then use the mass rate from the Venturi along with the percentage holdups from the nuclear system, combined with the processing power of the flow computer to give us volumetric flow rates in standard conditions. So with our gamma detector, how do we quantify the phase fractions? Well, it's ultimately very simple. On a production setting, where we currently have over 200 meters installed in America, we calibrate the meter to a physical water, a physical oil, and most often a compositional analysis of what gas is flowing. By having 3 calibration points, we obtain a triangle which encompasses the operating point depending on what the flow conditions are. This operating point is very dynamic and moves all within the triangle. As an example, if the operating dot, the little black dot in the center of the triangle, would be on the bottom left of the graph, right on the water point, it would be 100% pure water. This type of triangle is perfect in a production setting, but what does it actually look like if we want to quantify sand on a drill out? Well, here again, it's pretty simple. On a plug drill out, we expect 0 oil as long as we're in a balanced operation. There's some exceptions, but ideally we don't like to see any oil. We now construct a triangle using gas, water, and sand instead of gas, oil, and water. The operating point is still very dynamic. It moves within the confines of the boundaries established. And we can, in some circumstances, go back in time and come up with a 4-phase measurement. This just involves some post-processing by our domain team. So a typical rig up using a multi-phase meter ultimately results in very minimal change to a common setup. In situations where the shut-in pressure is above 5,000 psi, the working pressure of the meter, we like to be installed downstream of the choke manifold. This allows us to measure water, gas, and sand. However, it ultimately allows for safer operations in the higher pressure environments. Whenever we have a well that is below 5,000 psi, we very much like to be in between the plug catcher and the choke manifold, as shown in the image on the right, as this allows for a little bit smoother flow rates through the meter, higher flowing pressures, and lower gas breakout, which ultimately results in lower velocities throughout the meter. Both options have been used in the field, and both options yield excellent data. Ultimately, the rig up is very flexible and comes down to operator preference. Just a note, if there was ever a sand trap to be involved, we of course would like to be upstream of that, just so we can quantify all the sand that's coming from the wellbore. So let's take a quick look at some drone footage that shows how a VX meter is rigged up downstream of the plug catcher and upstream of the choke manifold. This footage was obtained on one of our latest mill-out operations in West Texas. So now that we've seen what the VX meter looks like when it's rigged up, what type of data does this meter actually provide? Here shown is actually a screen recording on one of our last jobs. This data, it's not only being shown in the Schlumberger Command Center, but we also transmit this to the company man shack, the coil tubing doghouse, and even flowback. This is a loop of a video, but we can see the VX meter keeps track of the sand rate, gas rate, and water rate, along with the wellhead pressure and the VX pressure. This real-time data allows everybody on location to be 100% knowledgeable of what is returning on surface. We can see here that during the course of the 15 minutes, water rate dips off substantially, only because the sand rate increases from nearly nothing to over half a barrel a minute. This real-time transmission of data allows us and flowback to make decisions in regards to plug catcher management, choke management, and the insight to know if a flaring operation needs to start should the gas rate warrant it. Here's a snapshot on one of our jobs, nearly identical to the previous video that we've seen, where the pink line represents an increase in sand and the blue line represents a drop in water. We can see the black line, the wellhead pressure, is slowly dropping before the sand slug comes to surface. We can infer that the circulating pressure during this time was also increasing as a column of sand was being mobilized up and out of the wellbore. Once the sand slug made its way to surface, the pressure slowly rises as the sand drops off. along with the water rate eventually returning to normal. The data here prepared the flowback crew on surface by alerting them that a hit of sand was imminent, and they could prepare by having personnel standing by on the plug catcher and choke manifold to make adjustments if needed. Here we can see a video animation of nearly the same event, except here we see a spike in gas, the orange line, before the sand reaches surface. This type of data really allows the whole pad to understand what is happening on surface, as previously this data was not available outside of sending flow into a separator. So one of the main benefits of using a VX meter on a plug drill out is the ability to get accurate water return rates, especially when flowback is unable to, in the traditional sense of strapping a tank. As flowback starts to fill up the surface tanks with fluid, sand begins to pile up below the gas buster, forming a large pyramid of sand at the bottom of the tank. When sand is on the bottom of this tank and fluid is rising over that pyramid, the rates measured by the strap stick are not accurate, as you're no longer getting rates for a rectangular vessel of water, but now something with sand as interference. You can see in the drawing on the right, if the water is filling up between the bottom of the tank and the top of the orange line, the measured water rate would be overestimated. Its strap would only become accurate once the water level has crossed over that peak of the sand mound. One could say that you could always ensure the water level is above the level of the sand to get an accurate strap, but this is not easy in practice, as surface tanks need to constantly be equalized to prevent overflowing. One of the issues at the end of the job is that flowback needs to give an estimation of how much sand was produced for that well, and it can be very hard depending on what the sand looks like on the inside of that tank. One person's judgment of sand volumes would be completely different than another person's. The beauty here is that by having a multi-phase meter, we can quantify during and at the end of the job exactly how much sand was produced throughout the course of the operation. Clients even use the multi-phase data to ensure that they are not being overcharged by vacuum trucks when hauling sand out of the location. So here's another operational picture where you can see the client was nominally flowing 4.5 barrels a minute and activated a hydro sweep to increase the pump rate to 6 barrels a minute. This increase in rate helps mobilize the sand that was stuck in the lateral or the heel by increasing the Reynolds number. Using this type of data, the client was confident that just by increasing their injection rate, they were able to mobilize sand that was stuck in the wellbore, allowing them to avoid a wiper trip, pumping a pill, and to ultimately keep moving downhole without ever having to pull out and risk getting stuck. This high-frequency data allows them to ensure that the wellhead pressure rates have returned to normal, sand and gas is mitigated on surface, and water rates are on target with where they should be. This practice, by increasing the Reynolds number to mobilize sand, has allowed a lot of our operators to reduce the footage from coil tubing and to ultimately reduce the total time spent in hole while milling out. Another great use of the multi-phase meter when installed between the plug catcher and the manifold is that we are able to monitor both the wellhead pressure and the VX pressure to see if there is any restriction in the lines. The multi-phase meter is equipped with numerous pressure sensors that we connect to parts of the flow line to allow us to have a better picture of what's going on throughout the rig up. Here we can see from the black line that wellhead pressure is pretty much maintained, however downstream pressure in green started to drop off. This differential pressure was purely caused by the plug catcher getting full of plug parts. We can see at the time 1635, once the clogged side of the plug catcher was swapped, the downstream pressure returned back to normal, and you actually see a small little increase in the water rate due to less flow restriction. Had the multi-phase meter not been out there, and had the flowback crew been occupied with other tasks, this event may not have been observed, ultimately resulting in the plug catcher being clogged and potentially even backing up into the upstream 3-inch iron, which would have caused the operations to cease in order to remove the obstructions. So one of the cool things by having high-frequency data available at your fingertips is the ability to see when every plug has been milled out and has returned to surface. Traditionally, operators would have flowback personnel pull screens to verify that a plug has made it back on time. On the graph shown, the white lines are the sand return rates. By having high-frequency data, you can visually see when plug parts and sand have returned to surface, reducing the amount of time that flowback has to be pulling screens, reducing HSE risk as most plug catchers allow for multiple plugs to be caught before interventions are needed. This gives you real-time data knowing that you don't have any sucking zones by knowing that flowback in the VX has an accurate return rate, and also the confidence to know that your wellbore is being cleaned out to prevent any issues once coil starts returning to surface. So this graph here highlights some of the HSE benefits by having a multi-phase meter. The blue line is the water line. We can see at the beginning of the job, flowback was returning 1 barrel a minute as coil was running in hole in the vertical. Once the bottom hole had been made lateral, the operator wanted to have a return rate. We can see in the beginning at around 12:30, a choke was chosen that was not the correct size. By having the multi-phase meter, within 5 minutes, they were able to analyze that choke was too big and a smaller choke was needed to be replaced in the manifold. This saved precious time by getting the return rates normalized to where they should be. You can see they fought choke sizes all the way until about 1:10 p.m., where they found a choke gave them the turn rates that was needed. Not only did the multi-phase meter make a quick job on finding what choke was needed to get the optimum return rates, but it also prevented somebody from strapping an open-top tank where nearly 500,000 scuffs of gas was being returned in orange. This is ultimately a summary graph shown here. Throughout the day and a half of the job, we can see that the water rate in blue was on average 3.7 barrels a minute. The drops were when the choke manifold was shut in, and this is a drill out using a stick pipe for reference. The gas rate in yellow showed an average return of 165 scuffs per day. By the end of the job, 111 barrels of sand was returned to surface. This big picture allows engineers in the office to know that the return rate was where it needed to be, gas was nothing crazy, and that the sand that was produced was in line with what they could and should expect. There are lots of data to be analyzed here. How much sand possibly came back from each zone? Was a particular zone over or under balance that may have led to that sand mobilization? How much gas was produced at the end of the job for reporting to necessary state agencies? Lots of stuff to be had here. One of the great things we have learned by using this high frequency data is that we can help ensure fractures are not damaged during the mill out operations. Here we can see around 7:20 a.m., the blue water return rate started to creep up just after a spike in gas was observed. We can assume that the combination of gas and proppant returning on surface had washed out the choke. By having this high frequency data, we identified water rates were increasing, and we were able to inform flowback that their choke was washing out and they needed to replace it. Had the VX not been out there, and had flowback not been informed this potential increase in rate could have continued until the next time a tank strap was done, and possibly even further out, as a tank strap would have been double checked as the return rates were not on target. By having the VX meter, we can identify any issues and help return operations to normal as soon as possible. So the multi-phase meter, it has a very great track record that we're pretty proud of. This meter has been utilized all over North America, specifically in nearly every basin where oil is produced in the United States. This meter allows for greater communication on site, reduces the amount of time somebody needs to be standing on top of a gassy open-top tank, and ultimately reduces the HSE risk. This VX meter has been used on over 400 plug mill-out operations across the United States, and we have yet to encounter any stuck events due to inadequate returns coming from downhole. This combination of experience between operations management, sales, and field personnel is greater than 20 years. You can ensure that you have the Schlumberger expertise to back up your operation. We have heard from numerous clients that they see 10-20% reduction in mill-out times by using the real-time data and allowing them to understand if wiper trips are needed or if they can continue moving along downhole. By ensuring rates are on balance, you avoid fracture damage while maximizing the well productivity by leaving that precious proppant downhole. This advantage, along with real-time quantification of flow rates, sand, and even emissions, can allow your operations to constantly improve to ensure that the most efficient plug drill-out operations are done. So as we get closer to concluding, I'd like to thank everybody for their time. Here's a slide showing multiple SPE articles that Schlumberger has published in regards to using the meter on mill-out operations, as well as some case studies that we have at slb.com. This presentation, I believe, is going to be distributed within the week to all the attendees, so you can always go back and reference these values. So here I'd like to take a moment to show the Schlumberger support team that we have in place. Myself, Michael Mikovic, I coordinate all operations for the multi-phase meter in North America. Lee View, my manager, he's the business unit manager for all of testing in North America, as well as sales. Justin Thompson, he's our sales engineer, mainly for Texas, Scoop and Stack, and some other areas. Ryan Williams, the OneStem Technology Domain Manager for North America, as presented earlier. Catherine Laconda, she is our resident domain champion out of Houston. And Caitlin, she is our sales engineer for the Rockies and Canada, as well as some other areas within the United States. So I would really like to thank everybody for their time. Thank you so much.
Thank you very much.